Okay, we're on page 5 of the notes, and now we're going to do some examples with the ratio test. So it says, use the ratio test to determine if the series converges or converges. So the way the ratio test is done is we say the limit as n goes to infinity of the absolute value of a to the n plus 1 over a sub n equals the limit as n tends towards infinity. So anywhere where there's an n, I'm going to replace each and every n in the numerator with n plus 1 and in the denominator with n plus 1 to fulfill the a to the n plus 1 requirement. And then I'm going to divide it by the original a sub n. So this is going to look like x to the 2 times n plus 1 all over n plus 1 factorial divided by x to the 2n plus 1 over n factorial. So we're going to have to use some rules of exponentials and factorials to simplify. But first I'll start with flipping the guy and distributing. So 2n plus 2 plus 1 simplifies to x to the 2n plus 3 times, flip the guy, n factorial in the numerator divided by, we have n plus 1 factorial in the bottom, and then x to the 2n plus 1. So we're going to simplify first using rules of exponents. So this gives me the limit as n goes to infinity. What am I left with? Subtract this from this. I get x to the 2, or x squared. N factorial over n plus 1 factorial leaves me with n plus 1 in the bottom. Now as you can see, x squared has no n's in it, so we're going to move it in front. It doesn't involve n, so really the only limit that I have to solve is this absolute value of n plus 1. Okay, so I see that as n goes to infinity, this is going to go towards 0. So what do I have? I have x squared times 0. But I know that this is always going to be 0, and that's my L. That's my result from the ratio test. So since L is less than 0 for all x, always, it doesn't matter what I pick for x, I'm going to multiply it by 0, so it's going to be 0. Then a sub n converges. In fact, let's go on and let's see what this means in terms of interval of convergence and radius of convergence. Since any value of x makes x squared times 0 equal to 0, then we can say that the IOC, the interval of convergence, is every x value, all real numbers. So minus infinity is less than x is less than infinity, and that the radius of convergence is infinity as well. Let's move on to the next example. Find this. This time we're asking to find the radius of convergence. So when you're faced with this situation, you're going to run the ratio test. This will give you the interval of convergence, and then from the interval of convergence you can find the radius of convergence. So we're going to take the limit as n goes to infinity of a sub n plus 1 over a sub n. Again, everywhere we see an n, we're going to replace it with n plus 1 for the a sub n plus 1 part. So n goes to infinity. Draw out our absolute value signs. It's going to be x to the n plus 1, the square root of n plus 1, divided by 3 to the n plus 1. That's my a to the n plus 1, divided by my a sub n is my original, x to the n, square roots of n, 3 to the n. So I left too much room here, but that's okay. Maybe I can. So I'm going to say equals the limit as n goes to infinity. So I'm going to flip the guy. So I've got x to the n plus 1, square root of n plus 1, all over 3 to the n plus 1, and then times 3 to the n in the top, x to the n, square roots of n. So again, I'm going to use my rules of exponents for the things that are in common. So I can write the limit as n goes to infinity. So if I compare this and this, I'm left with an x in the top. If I compare this and this, I'm left with a 3 in the bottom. Now, this and this, they're all the square root, so I can write that as 1 square root n plus 1 over n. Now, like before, whatever inside that does not have an n can get moved out front. So we're going to move this absolute value of x over 3 to the front. So this becomes the absolute value of x. You can write it over 3 or over the absolute value of 3. Either way is fine. This becomes the limit as n tends to infinity of the square root of n plus 1 over n, which we can further simplify because this over this plus this over this. So this is going to equal the absolute value of x over 3 is equal to the limit as n goes to infinity, square root of 1 plus 1 over n. Now remember, this is going to equal L. This term is going to go to 0, so this limit is going to always be equal to 1. So we have 1 times the absolute value of x over 3. Now, in order for us to converge, we always want this to be less than 1 to converge. So we're going to solve this inequality. So this times this is 1. And then we can remove the absolute value signs by doing this. Now we get x by itself, which would require us to multiply both sides by 3. So negative 3 less than x less than 3 is our IOC, our interval of convergence. If I plot my interval of convergence, I'm going to plot an open circle, I'm going to fill it in. The original question asks us to find the radius of convergence. So I'm going to draw a line. I'm going to draw an arrow from the center of the interval to one of the endpoints. And if I used a tape measure, I'd find that the radius of convergence is 3 units long. And in case you missed that very last line, I'll move my paper up just a little bit. You can see that I multiplied both sides by 3, and then this 3 canceled this 3. Okay. The last example that we're going to do is the ratio test to determine if the series converges or diverges, and we're going to follow the same process that we've been using. Again, radius of convergence, we're going to run the ratio test, which will give us our IOC, and our IOC will lead us to our radius of convergence. Okay, so we're going to take the limit as n goes to infinity, the absolute value of a to the n plus 1 over a to the n is the limit of n plus 1 factorial, x to the n plus 1, all over n factorial x to the n, which is just the limit as n goes to infinity. If I simplify this and this, I'm left with x, and if I simplify this and this, I'm left with n plus 1. And just like before, x, and there's no n in x, so I can bring that in front. So I'm left with x times the limit as n goes to infinity of n plus 1. Now, I want this thing to converge, but here's our problem, right? This limit is going to equal infinity. So we need to get x times infinity less than 1 to converge using the ratio test. So there is only one value of x. That will make 0 or x times infinity less than 1, and that is when x is 0. So to answer the question, the interval of convergence is going to be x equals 0. So when I plot that, I get 0, and I put a closed circle. So to follow my process to draw the radius of convergence, I don't go anywhere. So our conclusion is that when we only have a single point where we converge, our radius of convergence is 0. So those are some pretty good examples for the ratio test. So a couple more things before I end this video. We're in section 9.5 going to talk about endpoint convergence. So if I circle back to one of these previous examples, our interval of convergence is a test for absolute convergence. But what we're going to look at in section 9.5 is, do we converge at the endpoint -3 and or at the endpoint of 3? That's what we'll be investigating. So when we do go through this in section 9.5, the ratio test, which is a test for absolute convergence, establishes the radius of convergence and the interval of convergence. Theorem 5 guarantees us this is the same as the radius of convergence for this. So the absolute value and the series without the absolute value is the same. All that remains is to investigate the convergence of the endpoints of the convergence interval when the radius of convergence is finite, a finite non-zero number, just like in that other example I just pulled up. Okay, now I'm going to cross 3 and 4 out, but I do want to take the time to circle back and talk about the series 1 over n and 1 over n squared. And I want you to, I guess, relate this back to what we learned about the ratio test. Recall that when the ratio test yields a result where L equals 1, we say that the test is inconclusive. So I want to run the ratio test on both these series, and then I want to use improper integrals from section 8 to see if we get numbers or not. And then you'll see why when L equals 1, the ratio test is inconclusive. So let's start with the first series. I take the limit as n goes to infinity, a to the n plus 1 over a to the n equals the limit. So replace the n with n plus 1. I get 1 over n plus 1 plus over 1 over n. And then I'm going to flip the guy. I get n over n plus 1. So L'Hopital, infinity over infinity. I get infinity over infinity, run L'Hopital's rule, and I get 1 over 1. So this limit is 1. That's L. So we're inconclusive. Let's run the test also on the other series. So if I take the limit as n goes to infinity, a to the n plus 1 over a to the n, that's going to be the limit of 1 over n plus 1 squared over 1 over n squared. Take the limit, I get n squared over n squared, n squared plus 2n plus 1. So we get infinity over infinity, we run L'Hopital, we get 2n over 2n plus 2, which is again infinity over infinity, so I run L'Hopital again, I get 2 over 2, which is 1. So that's our L, and again we're inconclusive. I'm just going to abbreviate. So now we're supposed to use improper integrals to find the areas. And recall from chapter 8 is if we followed that process and we got a number, we converged, and if we did not come up with a number, we diverged. So we're going to go ahead and set it up. The limit as b goes to infinity, it will be improper, 1 to b, 1 over n dn. So we know that this is going to be the natural log of n, and we're going to evaluate that from 1 to b. So we get the limit as b goes